Alright, what's going on, physics? This might be a bit of a long one, so buckle up and get ready. So we have a wooden plank like this attached by a cable. Here's my wall over here. Plank is 5 meters long. This is on the slides. It's on slide 49 as of now. Plank is 5 meters long. Tells you the center of mass is located 2 meters from the left. So I drew that out for you. And yeah, you guys can see, so that's good. It says there's a hinge. So let's just jump right into it. So the mass of this is 225 kilograms. And the problem doesn't explicitly say this, but we're in equilibrium. It's not going anywhere. So because we're in equilibrium, three things are going to be equal to 0. The sum of my forces in the y direction equals 0. Sum of my forces in the x direction equals 0. And lastly, the sum of what? What else has to equal 0 if I'm in static equilibrium? If I'm not rotating, the sum of what would be 0 if there's no angular acceleration? The sum of my torques would have to equal 0. So this is the first step you can do in any static equilibrium problem. You can set all of these things equal to 0. From there, we can draw our forces. It's always important to label your forces in a problem. So let me do that. I have a force tension right here. Right, there's tension in this cable helping to keep the wooden plank up. So that's force T. And then there's gravity. Now this is an important point. I know 6th period already got started a little bit on this problem. We were asking, where should I draw force gravity from? It came up, some people thought maybe from the edge of this plank. But because it says the center of mass is located right here at this point, 2 meters from the left of the wall. Remember, the center of mass is the same thing as the center of gravity. It's the point where all of the force gravity seems to act. So I'm going to draw force gravity right here at the center of mass or the center of gravity. This is force gravity. So you look at this free body diagram. We have force tension, and we have going this way, force gravity going down. So ask yourself, am I done with this free body diagram? Am I completely done? Did I get all my forces, or are there more forces? So that'll be your question in 1 second. But I want you to think about it. We're in static equilibrium. All my forces in the y cancel, forces x cancel, and torques cancel. Look at this tension here. Right? This tension has an x component. Okay? If I had my free body diagram just like this, with only force gravity and force tension, tension has an x component going left. Which way would this system be accelerating if I said these are my only forces acting on it? Which direction would it be accelerating? If these were the only two forces, then this plank would be accelerating to the left, right? There would be an unbalanced force, the x component of tension, going left, and that's not the case. So that's proof right there that this hinge that's nailed into the wall, this has to apply a force. The force of this hinge, at least part of it. Alright guys, sorry about that. My video cut out, so just ignore this stuff in orange for now. As I was saying, the hinge has to apply a force. I'm just going to call it force H for hinge, because we're in static equilibrium and something has to cancel out the x component of tension here. So in order to cancel out the x component of tension, which direction, or at least partially, which direction should the force of the hinge point? Alright, so answer that now. Which direction should the force of the hinge point to cancel out the x component of this tension? Yeah, the hinge should point partially to the right in order to cancel out the x component pointing left from tension. Now I also drew it up just because it's going to be helping hold this plank in place, and we'll see later how to show that this is also pointing up. But now remember, in class we said we can pick an axis of rotation, right? We can pick whatever place we want to be our pivot point. So I look at this problem and I'm solving for force tension, all right? That's the first thing I want to solve for. So the smart thing to do when picking an axis of rotation or a pivot point is to get rid of things that you don't know. So I want to find the force tension, and I know my force gravity, right? It tells me the mass times gravity is force gravity, but I don't know anything at all about the force of this hinge. I have no clue. The problem doesn't tell me anything about it. So where should I place my axis of rotation in this problem? Well, I should place it on the hinge, and that's what I was covering up. I'm going to, in the orange here, I know it's smudged now, this axis of rotation, I'm going to place it right on the hinge. This way, I don't have to worry about this force right now. I can worry about that later. So let's start setting up the equations and going through the math. So we'll start with the sum of our torques. All right, the sum of our torques has to be 0. So I'm just going to start plugging in my forces and plugging in my torques. So we can pick either way we want to be positive. I'm going to say counterclockwise is positive. So if that's the case, I'm going to look at force tension. This torque from the force tension is positive. It's going to make it want to spin in this counterclockwise direction. So that's a positive force tension. And remember, it has to be the perpendicular component. Only the perpendicular part of the force is going to apply torque. So here's my angle. I want the perpendicular component, the piece right here. How would I find that given this angle? What trig function would I have to use? So I would use sine. Force tension sine 25. That's the perpendicular part of force tension. And torques are force perpendicular times the radius. What's the radius, or how far away is this force tension acting? How far away is it from the pivot point or the axis of rotation? It's 5 meters away, so make that a 5. And then, so that's our torque from the force tension. Now our torque from force gravity, that's going to spin it this way. It's going to spin it clockwise. So that's a negative torque. The force gravity, or mg, and mass was 225, so I'm just going to write that here. 225 times 9.8. So this is the force, this is force gravity, and then times the radius. What's the radius? How far away is the force gravity acting from that axis of rotation? The problem told me it's 2 meters away. So if it's not clear, this is force times radius, and this is force times radius. And of course, it has to be the perpendicular components of those forces. Now, all of gravity is perpendicular, so I don't have to worry about any trig functions for that. It's going to equal 0 because we're in static equilibrium. So I can just add this over. I have force tension, sine 25 times 5 equals 225 times 9.8 times 2. Solving for force tension, divide both sides by sine 25 times 5. Divide by sine 25 times 5. Let's type that in our calculators. I encourage you to do the same. Actually, right now, you type that in your calculator. Tell me what the answer is. I'll make it a net puzzle question, and then in 1 second, I'll tell you what the answer is. So the answer you should get is 2,086.99 newtons. So we just found our force tension. Our force tension, we used torque to find that. We put the axis of rotation on the force from the hinge, so we didn't have to worry about it. And then we were able to use torque to find the force tension. So let me go ahead and box this in case we need to look at it later. So that's the first part. We found force tension. We're good. The next part of the problem wants me to find the reaction force at the hinge. So what is the force of the hinge? So obviously, if you leave the axis of rotation on the hinge, you wouldn't be able to find any information because that would just be 0 with the torques. Although, remember, we have these 3 equations to work with. We have some of the forces in the y 0, some of the forces in the x and 0, and some of my torques is 0. So you can do a couple different things to find the force from the hinge. You could do torque. I actually didn't do torque at first, but let's go with torque and see what happens. Let's place my axis of rotation let's just call it right here. Let's say this is my axis of rotation. Okay? So now I'm saying this is my new axis of rotation. And the cool thing with these problems is you can pick whatever you want. If it doesn't work out, pick a different place. Just go with it, all right? On an AP test, just try. If you get stuck, try something new. So we're looking for the force of my hinge. Let's do the sum of my torques equals 0. Okay, so I'm going to go with counterclockwise. It's positive still, so we're still saying counterclockwise is positive. So if I look at the force of my hinge, and this is exactly what I'm saying. I look now, I would need the perpendicular component of the force of this hinge. I don't have an angle here. Okay, I have no angle here, so that's actually not going to help me. I don't know enough information. I can't work with my torques. All right, so if you get stuck on a problem like that on an AP test, recognize, okay, that's not the right way to go. Let's try a new direction. So I actually can't use torques to find this answer. We have no angle, so that means we're going to have to find our x component of this force hinge and our y component of that force hinge. And remember, from the beginning of the year, the square root of x squared plus y squared, that'll give you the answer. So let's look at the sum of our forces. Let's look at the sum of our forces in the y direction. Okay? So everything going up, I'll just call up positive. We have force tension sine 25, right? The y component is going up, plus the y component of the hinge minus the force gravity because that's going down. That'll equal 0. So let's get the force hinge y component alone. We have the force of the hinge in the y direction. It's going to be equal to, I add force gravity over, and then I subtract Ft sine 25 over. Let's plug in my numbers. The force of the hinge in the y direction is equal to mass times gravity. That's 225 times 9.8 minus the tension, 2086.99 sine 25. Type that in my calculator. You guys do this as well. What does the y component of the hinge equal? Find the y component of the hinge equals 1,323 newtons. I'll circle this because we need it later. Now, let's look in the x direction. Let's do the sum of my forces in the x direction. So this was torque. This was the y direction. Now we're going to look at the x direction. And I think I'll have enough room if I do it down here. So sum of my forces in the x direction equals 0. So in the x direction, we have force tension cosine 25, right? That would be the x component. There is no x component of force gravity. And then, because these are going opposite directions, Ft cosine 25 would have to equal the force of the hinge in the x direction. Right, we already said this earlier. The x component of this hinge would have to cancel that out. So let's plug in my numbers. Force tension was 2086.99 cosine 25. That will give me the x component of my hinge. So type that in your calculator. Let me know what you get. I got 1,891.5 newtons. So then I'll box this for you guys. And then to get my answer, to figure out what the force from the hinge is, we do the square root of x squared plus y squared. So I'm going to plug that into my calculator. Here's my y component of the hinge. X component of the hinge. Type that in my calculator, and I get that the force of the hinge is equal to 2,308.26 newtons. Now, the problem didn't ask you for the angle. Of course, if you remember, to get the angle, all you would do is inverse tangent of the y component over the x component. So I know this problem has a lot that goes into it, and you might get trapped along the way. Just remember, keep going if you get stuck, and these are the three main equations you're going to be working with. You're going to pick axis of rotation that's convenient for you, and you're going to work in these three equations to try to find your answers, all right? Any questions, ask them in class, office hours, all those good things.